Okay, yeah. So welcome to this session. And today in this session, we will see how to solve a heat equation. As promised, I told you that I'll be proving all the required results and everything at the end of the video. Okay, so this is the dedicated session. So in this session, we will prove heat equation. Okay, what is the solution that we had obtained earlier, how we derive that. Okay, so now we consider a heat equation. Fine, that's given by del u over del t will be equal to c square and del u and then del x2, where x is between 0 to L. I'll write down capital L because that will be helpful, because every time I make mistake in this L, so I'll take help of this capital L. Okay, and t as usual greater than 0. Fine. And now we need here three conditions. Because two will be for here and one will be for this thing. So basically we need three conditions. So let me impose three conditions. So I have u 0 comma t equals to 0 and a u at the final end. Okay, so that will be again 0, and then I need one more. So u x comma 0 will be equal to my f of x. Okay, now you consider, to understand this thing, I'll consider a simple what we call a rod, or you can say a string, anything you can take. Okay, now just let me throw this. Suppose I have a rod, let us say this is my rod of length L. Okay, so rod of length L, this is placed. Okay, and what I'm doing, I'm saying that temperature at both the boundaries is 0. Okay, here temperature is also 0 and here is also temperature is 0, and in between I want to check the behavior. Okay, in between, what is this u of xt? Okay, this u of xt means temperature. Okay, so basically I want to see what will be my u of xt, the distribution of the temperature, what I need to find out. Okay, so as t moves, or at which point I'm checking here. Okay, what is the time? So I want to know the behavior of heat in this rod. Okay, where temperature at both the ends I have fixed 0. Right. So now to do this, let us consider. Okay, solution is given by variable separable method, so we will consider variable separable method. So let the solution be given by u of xt. So since this is variable separable method, means we need a function of variable x and a function of variable t. So suppose there are two functions, let us say f of x and then g of t. Fine, f of x and g of t, these are my two functions. Fine. So now I'll simply I have to solve this del u by del t equal to c square and del square u upon del x square. So what we can do, we can simply begin with, let's differentiate it. So I get del u over del t. So this one will give me f of x, and I'll write down here g dot t. Okay, this dot simply means this is partial derivative, but since I have two variables x and t, so for x I'll be using this dash thing, which you have already seen. I'm talking about this thing. Okay, this will stand for partial derivative with respect to x, and this will represent partial derivative with respect to t. Okay, so that will be our notation. Just for convenience and nothing else, you can even use both the dashes. That's perfectly fine. There is no objection at all. Now let me differentiate with respect to x. So I get del u by del x will give me here f dash x times g of t will remain here, and then I find double derivative or partial. So that will give me f double dash x times g of t. Okay, I have found these two, and now I'll substitute in the original heat equation. Okay, here in this equation I'll substitute now. Okay, and let me check what I get. So basically, let me substitute. So I'll write down here substituting in equation star. Okay, so substituting in star. Okay, so I'll be getting star is our del u by del t equal to c square times del u over del x square. Now consider this del u by del t. It was from the previous slide. Just let me see. Del u by del t was f of x and g dot t. Fine. So let's substitute here. So I get f of x into g dot t will be equal to c square and then f double dash x into g of t. All right. So now just take x at one place and c at another place. So I'll be getting, let me check. Yeah. So f double dash x upon, I'll take f of x here, and then g dot t upon c square and then g of t. Okay, this will be done. Fine. I'm just taking this to here and g dash t here. Fine. Now I'm saying these are a function of f is a function of x and g is a function of t, and I'm saying their ratios are equal, so they must be equal to some. Okay, they must be equal to some lambda. Okay, since these are functions of x, basically this is a function of x, this is a function of t, and they are equal. Okay, so I'm saying ratios of these two are equal, so they must be equal to some lambda, a constant. Okay, now everything depends upon lambda. It may be 0, it may be non-zero, greater than 0, less than 0. So we will consider all the cases, and out of all those cases we will see which is the favorable case that gives our solution to our heat equation. So that is what we need. Okay, so now let me take, so this implies I'll be getting f dash x upon f of x equal to lambda. Okay, so this guarantees f double dash x equal to lambda f of x. Okay, and this is one equation. Oh, not this one. I'll check here. So f dash x minus lambda f of x equal to 0. This is one equation. And now let me derive in terms of g dash, g dot. So when I have g dot t upon c square times g of t is also equal to lambda. So I'll be getting g dot t equal to c square and then g of t. So it will be g dot t minus c square and then g of t equal to 0. Well, this is my equation 2. Okay, and now from here comes all the cases. Okay, so let us suppose first case lambda is 0. Okay, suppose lambda is 0. Case 1. Okay, case 1, lambda is equal to 0. That means, so equation 1 and equation 2, equation 1 and equation 2 gets reduced to, since lambda is 0, that means I don't have this part. Okay, this part will be 0 completely, and even this part will be 0. So I'll be getting f double dash x equal to 0 and g dot t equal to 0. Okay, so I'm getting f double dash x equal to 0 and g dot t equal to 0. So this simply means I have here, since f double dash x equal to 0, that simply means my f of x would be a straight line. Okay, so I can say it will be c1x plus c2. Fine. After simple integration, nothing else, and g of t again will be some constant. Okay. Let me take c3. Fine. So that means I got a solution. U of xt will be equal to f of x into g of t. That is what the solution we expected. So I'm getting here c1x plus c2 times c3. This is one of the solution. Uxt, okay, is one of the solution. Is one of the solution. Later we will discard this. Don't worry. One of the solution. Okay, so these are favorable cases. Case 1 was lambda equal to 0. When lambda equal to 0, you are getting this solution. Now we will see whether this solution has the capacity to give us the solution or not. Okay, or hold the trivial conditions and everything. Okay, probably it may happen that it may even get 0. Fine. Or if you do not believe, then simply let me check this. Fine. See, if this is the solution, then it must satisfy boundary conditions. Okay, so let me do this. U 0 comma t equal to 0. Okay, this is the first condition. So now I'll apply it. So I'll be getting here, there is no t. Okay, in this solution, simply x. So just put, I'm getting c2 into c3 equal to 0. Fine. This c1 x will be 0, c2 into c3 equal to 0. This implies what? either C2 equal to 0 or C3 equal to 0. Fine. So just keep it here. But if I take C3 equal to 0, okay. So if C3 equal to 0, then u of x comma t will be equal to 0 is a trivial solution. Okay, is a trivial solution. Trivial in the sense zero solution. We want a non-zero solution. Fine. So that's why I told you this solution. This won't be solution. Fine. Later on, I'm saying one of the solution because I do not know whether this is holding the condition or not. I'll first find out all possible solutions and then I'll check which one holds true. Okay. So now I'll get basically a trivial solution when C3 is 0, and when C2 is 0, I'll apply another condition. I have another one. So if I apply another condition, so u of L comma t equal to 0. If I apply this, then I'll get, since C3 was 0, then we get a non-trivial solution. So here C3 is non-zero. Okay, that means C2 is 0. So if C2 is 0, then I'll be getting C1L into C3 equal to 0. Now, just now I said, since C3 cannot be equal to 0 and this is length, okay, length is also cannot be equal to 0. So ultimate part would be C1 is 0. This implies C1 is 0. So if C1 is 0, C1 is 0, okay, and C2 is 0, C3 cannot be 0. In all of the cases, you get only one thing, that solution is trivial. Okay, it's trivial. Okay, ux equal to 0 is a trivial solution. Okay, so this equation doesn't have the capacity to give what we need. Okay, so we will discard this case. Okay, discard this case. We don't need it. That means what? Our lambda cannot be 0. Okay, so now we will take case 2. Okay, so case 2 says what? Case 2, when lambda is some positive constant. Okay, let's say lambda is greater than 0. Okay, a positive constant. And now I have to deal with lambda. So for simplicity, I'll take lambda equal to k square. Okay, just for solution, nothing else. Okay, lambda equal to k square is again a positive constant. Okay, and I have to also assume that lambda is non-zero. So if lambda is non-zero, then k will not be 0. Okay, so now let me check this. So our equation and equation 2. Okay, equation 1 and equation 2 will become, let's see here, I have, yeah, so here lambda is k square. Okay, so ultimately I'll be getting, I'll write down the equation here only, okay, so that you see it. So if lambda is k square, then I'll be getting f double dash x minus k square times f of x equal to 0. And here I'll be getting, one second, I think here I forgot to write lambda. Okay, will be lambda times. Okay, it is lambda times. So please make a correction there. It is lambda times. Okay, so lambda will be basically, this equation will turn out to be g dot t minus lambda is k square. So k square times g of t equal to 0. Okay, and c square is again here. Yeah, so I got this equation. And now to solve these equations, okay, one must have studied how to solve these equations. So basically I'll consider them by operator method. Okay, so I'm getting here f double dash x minus k square f of x equal to 0, and at this side I'll take g dot t minus c square k square and then g of t equal to 0. Fine. Now to solve this equation, just consider operator method. So by operator method, so I'm sure you must have studied operator method. So let us say you get something like this. Let's say it's just a simple justification. Okay, by dx2 plus phi dy by dx plus y, okay, equals to some 0 or some r of x, better. Okay, then you can simply write down the same equation like this: d square upon dx2 plus phi d by dx plus 1 of y equal to r of x. Now this is a differential operator, so I can write down this d square plus phi d plus 1 y equal to r of x, and then you find its trivial homogeneous part and all non-homogeneous part, then you find its general solution. That's nothing but y particular plus y homogeneous. Okay, so that is nothing but the operator method that you have studied. Okay, so I assume that you must be knowing it. If you do not know, then watch my other videos of ODE session and PD. I have explained these things. Now, so I'll consider this thing to be equal to some since d I'll consider auxiliary equation. Okay, so I'll get here m2 minus k square equal to 0. So I'll be getting m equal to plus or minus k. These m are roots. Okay, roots of the equation. So basically, when I have a solution like this, then I have this solution given by f of x equal to okay c1 into e power x plus c2 e power minus x, c1 e power x plus c2 e power minus x, and this is done. And now I'll play with this one. So I'll be getting here basically this is just m. Okay, so m minus it will be c square k square okay equal to 0. So I'll be getting m equal to c square k square. I got two roots. So for this thing I'll get simply my g of t would be equal to okay c1 into e power c square k square t. Okay, let me not write c1 because I have already used. So I'll take c1, c2. I'll take another constant, say c3. Okay, constants you can take as many as you want. Okay, there is no restriction over this. Now I got f of x and g of t. So my solution would be u of x comma t would be equal to what? F of x into g of t. That's what I had expected. And I got f of x and g of t. So I'll write down this. So it's c1 e power x plus c2 e power minus x into c3 e power c square k square t. Okay, so I'm done with this. And now I have to check whether they hold the conditions good or not. So I'll apply the condition u0 to equal to 0. Let me check what I'm getting here. So let's apply the condition u0 comma t equals to 0. Fine. So at the place of x, I'll be putting here 0. So what I'm getting here is c1 plus c2 into c3 times okay e power c square k square t equal to 0. Okay, and now this quantity should not be equal to 0. Okay, because exponentials it will never give you 0 unless t is minus infinity. Okay, so this implies either you have c1 plus c2 equal to 0 or c3 equal to 0. Okay, and now here if c3 is 0, the same condition that I raised even, if c3 is 0 then I get c1 plus c2 equal to 0. Okay, sorry, if c3 is non-zero then I get c1 plus c2 equal to 0. Okay, and we know that if c1 plus c2, see it is e power x and e power minus x. Okay, so basically they cannot be 0 unless and until c1 and c2 are 0. Okay, so even in this case also you get a trivial solution. Okay, so u of x comma t equal to 0 okay is again a trivial solution in this case too. Okay, is a trivial solution. So ultimately this case also we have to discard. Okay, even this is not true even. Fine. And mainly a few people even take this thing to be cos hyperbolic, sine hyperbolic, which is perfectly correct because there are various methods. Okay, so this case is also discarded. Okay. Discard the case. That means what? Our lambda cannot be positive even. This case also we have to discard. Okay, because in this case also we got a trivial solution, but we need a non-trivial solution. So that will be given only when lambda is a negative. Okay, so case 3. Case 3 is nothing but when lambda is less than 0. So I can write down lambda to be equal to minus k square. Okay, this will be again negative. Okay, so let lambda equal to minus k square, a negative constant. So again, from equation 2, equation 2 is your star from equation 1 and 2. Okay. So from equation 1 and 2, you must be getting, I'll roll back to equation 1 and 2. Yeah, this is my equation 1 and equation 2. Now it will get changed to, okay, everything will remain same except since lambda is minus k square, so this sign will become plus and this sign will become plus. Okay, so I got these two equations. Now let us solve them. Okay, so let's consider it and solve. Okay, so f double dash x plus k square and lambda is f of x equal to 0. This is 1, and then I had g dot t, okay, plus k square c square g of t equal to 0. I had two equations, this is equation 1 and equation 2. Now let us solve them. So again, by operator method, I'll be getting here m square plus k square equal to 0. So that will give me m equal to plus or minus k I. When roots are complex, then solution is given by these are complex roots. So basically I'll be getting c1 cos kx plus c2 sine kx into e power, here the real part, but real part is 0, so that will give me just 1. So I'm happy with this. F of x is c1 cos x and c2 sine kx, and here I'll play with this g dot t. Okay, so let's see what this can give us basically. Okay, so if I have here g dot t plus k square c square g of t, I can simply take this g dot t equal to minus k square c square g of t and bring back g of t here and simply integrate it to get the equation. Okay. Equal to minus k square c square. So if I integrate, then I'll get here ln of, okay, g of t would be equal to minus k square c square plus some another constant, say a. Okay, that's integral constant. Now I'll take g of t here. So this part will become e power minus k square c square plus a. I'm sorry, t will also come. I forgot this t. When I integrate this, I'll be getting here t also, okay, because I'm integrating with respect to t. Okay, so my solution would look like g of t equal to this e power a. I'll separate and I'll get another constant, say c3, and then e power minus k square c square t. Okay, so I got even this thing. Okay, so that part is done. Now let us write the solution. So u of xt is nothing but f of x into g of x. F of x into g of t, I'm sorry. So what is my f of x is c1 cos kx plus c2 sine kx, and then I have c3 times e power minus k square c square t. Okay, so I'm happy so far. This part is okay. And now comes the real thing. Okay, so let's begin. How to deal with the boundary conditions so far. Yeah, so my u of xt is nothing but c1 cos k, oh, 1 second. Yeah, c1 cos kx. I think something is missing here. That will be found, don't worry. Sine kx into c3 times, it was e power minus k square c square t minus k square c square t. Right? Now I can multiply this c3 and c1 inside to get another constant, and which I'll call by c4 times cos kx plus c5 times sine kx, okay, into e power minus k square c square t. Okay, so that is my u of xt. All right, and now I can simply apply the condition. So I'll be getting here u0 comma t was 0. Okay, so let's apply this condition to get this. when u0 t is 0, so this part right here will go away because x is 0, so this part will not come. So I'll be getting just c4 times c4 cos kx. So cos 0 is 1 and into, and this part will remain into the picture directly, and there is no objection at all. So this quantity will be equal to 0. Okay, and as I told you, this quantity will not be 0 unless and until t is infinity, t tends to infinity. So basically c4 is 0. Okay, so this implies c4 will be equal to 0. Okay, when your c4 is 0, then our equation boils down to u of xt equal to just c5 times sine kx into e power minus k square c square t. Okay, now I'll apply the another boundary condition. So I'll be getting u of lt equal to 0. Okay, oh, I'm sorry, this L was capital. This L was capital. Okay, so I'll be getting here, now apply the condition. So I'll be getting c5 times sine kl and e power minus k square c square t. Okay, c square k square t equal to 0. Now again the same thing will come. This quantity cannot be equal to 0, and if c5 is 0, if c5 here is 0, then we get again trivial solution. Okay, so I'll write down if c5 equal to 0, then solution is trivial. Okay, then solution is trivial. So I need a non-trivial solution. Okay, so for a non-trivial solution, for a non-trivial solution, I must have sine kl should be equal to 0. Okay, because this cannot be 0, this cannot be 0. Okay, write it down here. c5 should not be 0, and e power minus k square c square t is exponential, so it cannot be 0. So sine kl is 0. If sine kl is 0, this implies kl will be equal to n pi. Okay, kl will be equal to n pi. So basically you get k equal to n pi upon l. Okay, so that is my k. Now I'll substitute this k to in this equation. Okay, and then observe the reaction, what will happen here. Okay. So u of xt will now be equal to yeah, this is the solution, c5 sine kx e power minus k c square t. So let us substitute it here and let's check what we get here. Fine. So this c5 and then sine, we got here it was kx, but k was equal to n pi. Okay, so I get here n pi x, okay, upon l into e power minus c square, yeah, k square c square t, but k was n pi l, so it will be basically n square pi square upon l square. Okay, so let me write down, oh, rather let me write it down here only. So this part will become basically I'll use another ink just for my convenience. Yeah, so I get here e power minus n square pi square upon l square c square t. Okay, so it will become e power minus n square pi square c square upon l square t. Okay, this is what I found. Okay, and for the broad terms I'll write down so that it is visible to you. So u phi equal to c phi and then sine n pi x upon l into e power minus n square pi square upon l square, okay, and then c square t. Fine, this is what I found. And if you see, then this equation depends upon the n, okay, everywhere. So what is this n? Now if I have this thing n, so I can now find the solution for each n. Okay, so for different n I'll be getting different solutions. Okay, that means what? Okay, so this solution in fact can be particularly be generalized. Okay, this solution now can be generalized, and I say this is c phi. Okay, so if I place some other constant, then I'll be getting each and everything each time. Okay, so I can write down this in fact for different n I'm getting. So I'll say this is un of xt. okay, will be equal to this constant. I'll keep into the picture. I'll write down this Cn, okay, and then sine, okay, n pi x upon L, and then e power minus, okay, c square times n square pi square upon L square t. Okay, this is what I found. And now everything now depends upon the n. Fine. So now let's check. And here solution will run from n equal to 1, 2, 3, and so on. Okay, all positive integers. N will be all just positive integers. Okay, in our case. Okay, n will be positive because n here will not make any impact because everything here will depend upon t. So our goal is to find out a solution which, when limit t tends to infinity, should go to 0. Okay, our goal is to find out such a solution. So if this part will have no problem, but this part, if n is negative, then this part will basically tend to minus infinity, which will be wrong. Okay, uh, 1 second, there is some error here. Okay, yeah, so if you noticed, then I forgot to tell you this. um, there are certain things involved here. I'm saying n equal to 1 to 3 because here we got n pi upon L. Okay, but n pi upon L is the value of k, basically k equal to n pi upon L. But what is k? Okay, what is k? The rule comes from here. Okay, since lambda is negative, so k here, we had taken lambda was negative, so lambda equal to minus k square. But if I take n equal to 1 to 3 and everything, then this minus plays the role. Fine. Okay, so lambda will be negative. So if lambda should be negative, then I have to take k to be positive. Okay, so that's the only reason. It should be all start from n equal to 1 to 3 and all. Fine. So we got un equal to un of xt equal to cn sin n pi x upon L and e power minus c square n square pi square upon L square t. Now this is un of xt. So that means for each un I'll be getting a different solution. So that means what? Do I have infinitely many solutions for a heat equation? No. So there comes a principle of superposition. Okay, by principle of superposition. By principle of superposition. So superposition, in the sense, if you understand the meaning of superposition, so suppose there is a boy, okay, in school, and there are few other boys. Let's take boy 1 and boy 2 and boy 3, boy 4, boy 5, and let's take boy 6 and so on. There are many and many, fine, countably many, in fact. So let's say they are beating this person. So let's say this is boy P. Okay, so they are beating this. Okay, they are beating them. So each boy will try to put its own force to this boy. So they will beat this basically. So ultimate net result can be seen after all the forces are added together. Okay, net forces all added together, that you will get the net result. Okay, so suppose his body is broken, so that's the ultimate result of all these beatings that he had got. So it will be basically addition of all the fights that he had received. That we can say a principle of superposition. Superposition means each person is trying to show its force. Okay, behaving as if other boys are not there. Okay, other boys are not there. Just all of them will try to beat this boy. Okay, simply ignoring that rest of them are beating. So why should I beat? That's not the condition. They will beat. B1 will beat in its manner. Similarly, B2 will beat, and then B3 and all. Right. So basically, the net result will be his broken face. That's superposition. Okay. And I'm not disrespecting physics, but to understand this thing, you can take a simple example. Nothing else. Fine. So by principle of superposition, u of xt will be nothing but addition of all these solutions. So n equal to, and runs from 1 to infinity. So I'll be getting in from 1 to infinity un of x comma t. Okay, and if you just substitute here what is un of xt, then you get n equal to 1 to infinity, and then cn, and then sine of n pi x upon L, and then e power minus c square n square pi square upon L square times t. That is my u of x t. And now we have to find out this Cn. What is this Cn? Okay. So to find out this Cn, we have to use another condition that is given to us. Okay. So this is the solution of the heat equation. Okay. Is the solution of the heat equation. Solution of the heat equation. It's the same equation that I had written while solving heat equation problems. Okay. At the place of Cn, it was just dn because अच्छा लगता है simply. So it is Cn. Now let's find out this Cn. So we will use the initial condition that is given to us. So u of xt is nothing but summation of n equal to 1 to infinity Cn and then sine n pi x upon L and then e power minus c square. Okay, then it will be n square pi square upon L square and t. Fine. This is what we have found here. Yeah. Now let us use the condition since u of x comma 0 equal to some f of x. Okay, u of x comma 0 is given to be some f of x. That's our initial condition that is given to us. Now to apply this, at the place of t, we will put remaining things to be 0. So I'll be getting here f of x will be equal to summation n equal to 1 to infinity Cn and then sine n pi x upon L, and if I put here t to be 0, then this entire quantity will become 1. Okay, so this is a Fourier sine series. Okay, it is a Fourier sine series, which is a Fourier sine series. And this Cn is nothing but the Fourier coefficient, which is given by Cn equal to 2 upon L integral 0 to L f of x into sine n pi x upon L dx. This is nothing but the Fourier coefficient. So you found solution of the heat equation, and Cn is given by this quantity. Okay. So it solves your heat equation. So this was the most easiest solution that I could give. There are many solutions available on YouTube, even in books. Okay. And there are many methods. Even one method I have given by variable separable method. There are various methods like Fourier transform and Laplace transforms. Okay, there are many methods to solve this equation. Okay, so to solve heat equation, you can apply this easiest method, which is called as variable separable method. I hope things are making sense to you and you liked it. Thanks for watching.